On the 7th of January 1995, in a basement laboratory at the University of Colorado in Boulder, a team led by Eric Cornell and Carl Wieman achieved something that had been theoretically predicted 70 years earlier, but that many physicists had quietly suspected might never be realized in practice. They cooled a small cloud of rubidium atoms to a temperature so close to absolute zero that the atoms lost their individual identities. The cloud did not freeze in any conventional sense. It did not become a solid or a liquid or anything that the familiar vocabulary of everyday matter could adequately describe. Instead, the atoms underwent a phase transition into a new state of matter entirely, a Bose Einstein condensate, in which thousands of separate particles began behaving as a single quantum entity, their individual wave functions merging into one coherent whole that occupied the same quantum state simultaneously. The temperature at which this occurred was approximately 170 nanokelvin, 170 billionths of a degree above absolute zero, a temperature so far below anything that exists naturally in the known universe that even the void of deep space, at roughly 2.7 Kelvin, is millions of times warmer. This experiment, which would earn Cornell and Wieman the Nobel Prize in Physics in 2001, was not designed to answer questions about fire. It had nothing to do with combustion, or flames, or the transformation of burning gases into solid material. And yet the conditions it explored, the behavior of matter at temperatures approaching the theoretical basement of the thermodynamic scale, open a window onto a question that sounds absurd on its surface, but that turns out to be a serious inquiry into the nature of matter, energy, and the surprisingly negotiable boundary between what we call a gas, what we call a solid, and what we call fire. To understand why the question of whether fire can become a solid at sufficiently low temperatures is even coherent, you first need to understand what fire actually is. And this turns out to be considerably more complicated than most people assume. Fire is not a substance. This is the first and most important correction to the intuitive understanding of combustion. For most of human history, fire was understood as a thing, a material, an element. The ancient Greeks listed it alongside earth, water, and air as one of the four fundamental constituents of the universe. Heraclitus of Ephesus went further, arguing that fire was the primary substance from which all others were derived, a cosmic principle of change and transformation that underlay the apparent stability of the physical world. This was not a fringe position. It was a serious philosophical claim, and it persisted in various forms for more than 2,000 years, reaching its most sophisticated expression in the phlogiston theory of the 17th and 18th centuries, which proposed that combustible materials contained an invisible substance called phlogiston that was released during burning. The phlogiston theory was elegant, internally consistent, and wrong. It was dismantled by Antoine Lavoisier in the 1780s through a series of meticulous experiments that demonstrated what combustion actually is, a chemical reaction. Specifically, combustion is a rapid exothermic oxidation reaction, a process in which a fuel, typically a hydrocarbon or other organic compound, reacts with an oxidizer, typically molecular oxygen, to produce carbon dioxide, water, and energy in the form of heat and light. The flame that you see when you strike a match is not a substance being consumed or released. It is a region of space in which this chemical reaction is occurring, a zone where fuel molecules and oxygen molecules are colliding with sufficient energy to break their existing chemical bonds and form new ones, releasing the energy difference as electromagnetic radiation and thermal kinetic energy. The visible flame itself is composed primarily of incandescent gas and soot particles. The blue portion near the base of a candle flame is a region where combustion is relatively complete, with hydrocarbon molecules being broken down and recombined with oxygen efficiently enough that few solid carbon particles are produced. The temperature in this zone is typically between 1300 and 1400 degrees Celsius. The yellow-orange portion higher in the flame is a region where combustion is less complete, and tiny particles of solid carbon, soot, are heated to incandescence by the surrounding reaction, glowing with the characteristic warm color that we associate with firelight. These soot particles are typically between 10 and 50 nanometers in diameter, and they are already solid. They are solid carbon particles suspended in a hot gas, radiating visible light because their temperature is high enough to produce thermal radiation in the visible spectrum. This is a point worth pausing on, because it complicates the question in an interesting way. Fire is not a single phase of matter. It is a dynamic, multi-phase phenomenon. The hot gases in a flame are indeed gaseous, a turbulent mixture of nitrogen, carbon dioxide, water vapor, and various intermediate combustion products. But the luminous soot particles that give the flame much of its visible character are solid. Even in an ordinary candle flame, solid matter is present, glowing, and central to the visual experience of fire. The flame is not a gas pretending to be something else. It is a heterogeneous system containing gas phase reactants and products, liquid phase droplets in some combustion regimes, and solid phase particles, all coexisting in a reaction zone maintained by the continuous input of fuel and oxidizer. But this is not what the question is really asking. The question is asking something more radical. It is asking whether the gaseous components of a flame, the hot, fast-moving molecules that constitute the bulk of the combustion zone, could be cooled to the point where they undergo a phase transition to a solid state. And to answer that, you need to understand what phase transitions are, what determines the state of matter a substance occupies, and what happens to the chemistry of combustion at temperatures far below those at which it normally occurs. The state of matter that a substance occupies, whether it is solid, liquid, or gas, is determined by the balance between two competing tendencies: the kinetic energy of its constituent particles, which drives them apart and promotes disorder, and the intermolecular forces between those particles, which pull them together and promote order. At high temperatures, kinetic energy dominates and molecules move freely, giving rise to the gaseous state. At low temperatures, intermolecular forces dominate, and molecules lock into fixed positions relative to one another, giving rise to the solid state. The liquid state exists in the intermediate regime, where molecules have enough energy to move past one another, but not enough to escape one another's attractive influence entirely. Every substance has characteristic temperatures at which these transitions occur, its melting point and boiling point, which depend on the strength of its intermolecular forces and the pressure of its environment. Water freezes at 0 degrees Celsius and boils at 100 degrees Celsius at sea level. Nitrogen, with much weaker intermolecular forces, boils at minus 196 degrees Celsius and freezes at minus 210 degrees Celsius. Carbon dioxide, interestingly, does not have a liquid phase at normal atmospheric pressure. It sublimes directly from solid to gas at minus 78.5 degrees Celsius. At higher pressures, liquid carbon dioxide can exist, and this is exploited industrially in supercritical carbon dioxide extraction and in fire extinguishers. Now consider the products of combustion, the molecules that constitute the gaseous portion of a flame. The two primary products of complete hydrocarbon combustion are carbon dioxide and water. Both of these substances can exist as solids. Solid carbon dioxide, dry ice, is a familiar material used in theatrical effects, cold chain logistics, and countless high school science demonstrations. It is a white, opaque solid that sublimes at atmospheric pressure, producing the dense, cold fog that rolls across stage floors. Solid water is, of course, ice, the most familiar solid on Earth. Water freezes at 0 degrees Celsius under normal conditions. The intermediate products and byproducts of combustion are also capable of solidification. Carbon monoxide, produced by incomplete combustion, freezes at minus 205 degrees Celsius. Formaldehyde, another intermediate, freezes at minus 92 degrees Celsius. Various polycyclic aromatic hydrocarbons, the complex organic molecules that form in fuel-rich flame zones, have melting points ranging from 80 degrees Celsius for naphthalene to over 200 degrees for larger ring structures. And elemental carbon, the soot that gives flames their luminosity, is already solid, with a sublimation point of approximately 3600 degrees Celsius, one of the highest of any element. So the answer to the most literal version of the question is straightforward and perhaps disappointing. Yes, the chemical products of fire can be cooled until they become solid. Carbon dioxide becomes dry ice. Water becomes ice. Carbon monoxide freezes into a transparent, crystalline solid. Even the nitrogen and oxygen in the surrounding air will solidify at sufficiently low temperatures. If you could somehow capture the exhaust gases of a flame and cool them progressively, You would watch them condense and freeze in sequence, each component dropping out of the gas phase at its characteristic transition temperature, until you are left with a collection of solids at cryogenic temperatures. It is undergraduate chemistry, but the more interesting version of the question asks something different. It asks not whether the products of fire can be solidified, but whether fire itself, the process, the reaction, the dynamic phenomenon of combustion, can exist in a regime where its products are solid. Can there be a flame that produces solid carbon dioxide and solid water, directly, a combustion reaction that runs at temperatures below the freezing points of its own products? The answer to this requires a deeper engagement with the thermodynamics and kinetics of combustion than the simplified version of the question suggests. And it leads into territory that is genuinely surprising. Combustion is an exothermic reaction, meaning it releases energy. The heat released by the reaction is what maintains the high temperature of the flame, which in turn provides the activation energy needed to sustain the reaction in the incoming fuel and oxidizer. This is the feedback loop that keeps a fire burning. The flame heats the fuel, the hot fuel reacts with oxygen. The reaction releases heat, the heat sustains the flame. If any component of this loop is disrupted, the fire goes out. Remove the fuel and the reaction has no substrate. Remove the oxygen and the reaction has no oxidizer. Remove the heat, cool the reaction zone below the temperature needed to maintain the chain of chemical reactions, and the fire extinguishes itself. This is why fire cannot exist at very low temperatures in any ordinary sense. The chemistry of combustion requires a minimum temperature to proceed, because the fuel and oxidizer molecules need a certain amount of kinetic energy to overcome the activation energy barrier of the reaction. For most hydrocarbons burning in air, the minimum temperature for sustained combustion is between 200 and 300 degrees Celsius. Below this temperature, the reaction rate drops to effectively zero, and no flame can be maintained. There is no such thing as a cold fire in the conventional chemical sense, because fire is, by definition, a self-sustaining high-temperature chemical reaction. But there are phenomena that complicate this simple picture, and they point toward a more nuanced understanding of what combustion can look like under unusual conditions. The first complication is cool flames, a phenomenon that was first observed in the 1820s, and that remains an active area of research in combustion science. Cool flames are faint, barely luminous reaction zones that can propagate through fuel. Air mixtures at temperatures far below those of ordinary flames, typically between 200 and 400 degrees Celsius. They are associated with the low-temperature oxidation, chemistry of hydrocarbons, a complex network of chain, branching reactions involving peroxide, intermediates that can release enough energy to sustain a propagating reaction front without ever reaching the high temperatures of conventional combustion. Cool flames produce little visible light, sometimes just a pale blue glow detectable, only in darkened rooms, and they can exist in pressure and temperature regimes where ordinary flames cannot. They are not cold in any absolute sense, but they demonstrate that the boundary between combustion and non-combustion is not a sharp line, but a gradient, and that exothermic oxidation chemistry can occur at temperatures far below what we normally associate with fire. The second complication comes from combustion in exotic environments. In microgravity, where buoyancy-driven convection is absent, flames behave very differently than on Earth. Experiments conducted aboard the International Space Station have produced flames that burn at significantly lower temperatures than their terrestrial counterparts, forming spherical diffusion. Limited reaction zones that can sustain themselves at temperatures low enough that the flame is invisible to the naked eye. These microgravity flames are still far above cryogenic temperatures, but they demonstrate that the temperature of a flame is not fixed by the chemistry alone. It is also determined by the transport processes, the convection, diffusion, and radiation that carry heat and reactants to and from the reaction zone. Change the transport environment and you change the temperature at which the flame stabilizes. The third complication, and the one that takes us closest to the spirit of the original question, comes from chemistry under extreme cryogenic conditions. And here the physics becomes genuinely strange. At temperatures approaching absolute zero, chemistry does not simply stop. It changes character. Classical thermal chemistry, in which reactions are driven by the kinetic energy of colliding molecules, does indeed cease at very low temperatures, because the molecules are barely moving and collisions are too gentle to overcome activation energy barriers. But quantum chemistry can take over. At sufficiently low temperatures, the wave-like nature of particles becomes important, and reactions can proceed by quantum tunneling. The phenomenon in which a particle passes through an energy barrier that it does not have enough classical energy to surmount. The particle does not go over the barrier. It goes through it with a probability that depends on the barrier's height and width and on the particle's mass. Quantum tunneling reactions have been observed in the interstellar medium, where temperatures can drop to 10 or 15 Kelvin and where conventional chemistry should be impossible. In these cold molecular clouds, hydrogen atoms tunnel through energy barriers to react with other molecules, forming complex organic compounds that classical chemistry cannot explain at those temperatures. Carbon monoxide and other simple molecules participate in surface reactions on dust grains at temperatures of 10 to 20 Kelvin, assembling into more complex molecules through tunneling processes that would have zero probability in a classical framework. These are not combustion reactions in the traditional sense. They are not exothermic oxidation of fuel and oxygen, but they are chemical reactions. They involve the rearrangement of atoms and the formation and breaking of chemical bonds, and they occur at temperatures where every substance involved is either solid or adsorbed onto a solid surface. In 2011, a team of researchers at the University of Leeds demonstrated that the hydroxyl radical, one of the most important reactive species in combustion chemistry, could react with methanol at temperatures as low as 63 Kelvin through a quantum tunneling mechanism, and that the reaction rate actually increased as the temperature decreased, contrary to the predictions of classical chemical kinetics. This was a striking result because it suggested that certain oxidation reactions, the same class of reactions that underlie combustion, could proceed not just at cryogenic temperatures, but preferentially at cryogenic temperatures, exploiting quantum mechanical effects that are suppressed at higher temperatures by the dominance of classical thermal motion. This does not mean that a candle flame can burn at 63 Kelvin. The integrated, self-sustaining, macroscopic phenomenon that we call fire requires a feedback loop of heat generation and chemical activation that cannot be maintained at cryogenic temperatures. But it does mean that the individual chemical steps that constitute combustion, the breaking of carbon-hydrogen bonds, the formation of carbon-oxygen bonds, the oxidation of fuel molecules, can under the right conditions occur at temperatures where the reactants and products are solid. Oxygen freezes at minus 218.8 degrees Celsius, or 54.4 Kelvin. Methane freezes at minus 182.5 degrees Celsius, or 90.7 Kelvin. At temperatures below these points, both fuel and oxidizer are solid, and yet quantum tunneling chemistry can still proceed on the surfaces and within the bulk of these cryogenic solids, albeit at rates that bear no resemblance to the rapid, luminous, turbulent process we call fire. There is a context in which this kind of ultra-cold chemistry is not merely a laboratory curiosity, but a matter of considerable scientific importance, and that context is the chemistry of the outer solar system and the interstellar medium. The moons of Jupiter and Saturn, the surfaces of comets, the vast molecular clouds that fill the space between stars, all of these environments are cryogenic, and all of them contain the raw materials of combustion, hydrocarbons and oxidizers, frozen into solid matrices at temperatures ranging from 10 to 100 Kelvin. The chemistry that occurs in these environments is slow, driven by quantum tunneling and by the occasional input of energy from cosmic rays or ultraviolet radiation. But it is real, and it produces complex organic molecules that have been detected by spectroscopic observation, and in some cases, by direct analysis of return samples. The surface of Titan, Saturn's largest moon, presents a particularly striking example. Titan's surface temperature is approximately minus 179 degrees Celsius, or 94 Kelvin. At this temperature, water ice is as hard as granite and serves as the bedrock of the moon's geology. Methane, which is a gas on Earth, exists on Titan as a liquid, filling lakes and seas and falling as rain, playing the same hydrological role that water plays on our planet. The chemistry of Titan's atmosphere, driven by ultraviolet radiation from the distant sunday, produces complex organic molecules called tholins, reddish-brown polymers that settle onto the surface and accumulate in deposits that may be meters thick. These tholins are produced by reactions that include oxidation steps, not with molecular oxygen, which is absent from Titan's atmosphere, but with other oxidizers produced by photochemistry. The process is not fire. It does not involve rapid, self-sustaining exothermic combustion, but it is chemistry of the same fundamental type, the rearrangement of carbon, hydrogen, oxygen, and nitrogen atoms into new molecular configurations, occurring at temperatures where all of the reactants and products are either solid or liquid. The question of whether fire can become a solid at sufficiently low temperatures is, in the end, a question about how rigidly you define fire. If fire means the macroscopic, self-sustaining, luminous, exothermic combustion reaction that burns in a hearth or at the tip of a candle wick, then no, fire cannot become a solid, because that specific phenomenon requires temperatures far above the freezing point of any of its components. The flame goes out long before its products could freeze. If fire means the underlying chemistry of oxidation, the breaking of carbon-hydrogen bonds, and the formation of carbon-oxygen bonds that constitutes the molecular essence of combustion, then the answer is more nuanced. Those reactions can occur through quantum tunneling and surface chemistry at temperatures where everything involved is solid. The products of those reactions, carbon dioxide, water, carbon monoxide, are solid at those temperatures. The chemistry runs on solid substrates, produces solid products, and proceeds without anything that could be called a flame. But there is a third way to approach the question, and it is the one that a physicist might find most interesting. It involves not the chemistry of combustion, but the physics of phase transitions, and it asks what happens to matter itself at the lowest temperatures the universe allows. As temperature decreases toward absolute zero, matter does not simply become colder. It changes its fundamental character. The classical picture of atoms as tiny billiard balls bouncing off one another gives way to a quantum mechanical picture in which atoms are better described as wave packets smeared out over space. Their positions and momenta governed by the Heisenberg uncertainty principle. At sufficiently low temperatures, the de Broglie wavelength of an atom, the characteristic length scale of its quantum wave function, becomes comparable to the distance between neighboring atoms, and the quantum nature of the particles can no longer be ignored. The atoms begin to overlap, to interfere with one another, to behave collectively rather than individually. For bosonic atoms, particles whose quantum spin is an integer, this collective behavior leads to Bose, Einstein condensation, the phenomenon that Cornell and Feynman observed in their rubidium experiment. In a Bose-Einstein condensate, a macroscopic number of atoms occupy the same quantum state, losing their individual identities and behaving as a single coherent quantum object. The condensate has properties that are unlike any conventional state of matter. It can flow without friction, a property known as superfluidity. It exhibits quantum coherence on macroscopic scales, meaning that the wave-like behavior normally confined to subatomic particles becomes visible and measurable at the scale of laboratory apparatus. For fermionic atoms, particles whose spin is a half-integer, the low-temperature behavior is different but equally strange. Fermions cannot occupy the same quantum state due to the Pauli exclusion principle, so they do not condense in the same way. Instead, at very low temperatures, they can form Cooper pairs, bound states of two fermions that together behave as a boson and can then undergo a form of condensation. This is the mechanism underlying superconductivity in metals and superfluidity in helium. 3. These quantum states of matter do not fit neatly into the categories of solid, liquid, and gas. A Bose-Einstein condensate is not a solid, even though it exists at a temperature far below the freezing point of the material from which it is made. It is something else entirely, a state that the classical vocabulary of phase transitions was not designed to describe. A superfluid is not a liquid in the ordinary sense, even though it flows and fills containers. It is a quantum fluid with properties that have no classical analog. If you were to take the products of a combustion reaction, the carbon dioxide and water and carbon monoxide molecules produced by a fire, and cool them progressively toward absolute zero, you would first see them freeze into conventional solids, crystalline structures with atoms locked in regular lattices. Continue cooling, and the thermal vibrations of the atoms in those lattices would decrease, approaching the quantum mechanical zero-point energy, the irreducible minimum motion that the uncertainty principle demands. At the very lowest temperatures, some of these solids might exhibit quantum effects, anomalous thermal conductivity, quantum tunneling of atoms between lattice sites, isotope, dependent behavior that reflects the wave nature of the constituent particles. These effects have been observed in solid helium, which exhibits a range of quantum phenomena at temperatures below 1 Kelvin, and in solid hydrogen, which undergoes quantum rotational transitions that affect its thermodynamic properties in ways that are not predicted by classical solid state physics. Whether these quantum solids, these ultra-low temperature crystalline phases of combustion products, deserve to be described as fire that has become solid is a question of semantics as much as physics. The chemical identity of the molecules is the same. The carbon dioxide that was produced by a flame and the carbon dioxide that has been frozen into a solid crystal at 10 Kelvin are the same substance, with the same molecular structure and the same chemical bonds. The history of the molecule, the fact that it was born in a flame, does not affect its physical properties at low temperature. Fire does not become solid. The products of fire become solid. The process and the products are different things. And yet there is something in the original question that physics cannot entirely dismiss, something that touches on a genuine and unresolved tension in our understanding of matter and energy. The distinction between a process and a substance, between fire as an event and fire as a thing, has been a source of philosophical confusion for as long as humans have been thinking about the natural world. Heraclitus was not simply being poetic when he placed fire at the center of his cosmology. He was recognizing something that modern physics has confirmed in its own vocabulary. The universe is not made of things. It is made of processes. Particles are excitations of quantum fields. Atoms are dynamic configurations of quarks, and electrons held in patterns by forces. Solids are not static arrangements of fixed points. They are vibrating, tunneling, quantum mechanical systems, whose apparent stability is a consequence of the deep energy minima in which their constituent particles are trapped. From this perspective, the question of whether fire can become a solid is not a question about a specific chemical reaction at a specific temperature. It is a question about the nature of transformation itself, about whether the processes that define matter at high temperatures have analogs at low temperatures, about whether the dynamic reactive energy, releasing character of combustion, has any meaningful parallel in the quantum behavior of cryogenic solids. The answer is that it does, in the limited and specific sense that chemical reactions can occur in solids at cryogenic temperatures through quantum tunneling, and that the products of those reactions are themselves solids. But the deeper answer is that the vocabulary of solid, liquid, gas, and fire was developed to describe the macroscopic world of human experience, and it begins to break down at the extremes of temperature and scale where quantum mechanics becomes dominant. The coldest temperatures ever achieved in a laboratory are measured in picokelvins, trillionths of a degree above absolute zero, reached in experiments on nuclear spin systems and Bose-Einstein condensates in the early 2020s. At these temperatures, the concept of temperature itself becomes ambiguous because the systems in question are so far from thermal equilibrium that the statistical mechanical definition of temperature, which assumes a well-defined distribution of energy among a large number of particles, barely applies. In these regimes, the classical states of matter are irrelevant. There are no solids, no liquids, no gases in any conventional sense. There are quantum states, coherent and fragile, and utterly unlike anything in everyday experience. Fire, in these conditions, is not merely frozen. It is ontologically absent. The concept of combustion requires a thermal environment in which molecules have enough kinetic energy to collide and react, and at picokelvin temperatures, kinetic energy in the classical sense has effectively ceased to exist. The molecules do not move in the way that the word move implies. They occupy quantum states defined by their wave functions, and their behavior is governed not by collisions and trajectories, but by probabilities and superpositions. The chemistry that underlies fire requires a classical world of heat and motion and collision, and at the bottom of the thermodynamic scale, that classical world has been replaced by something fundamentally different. What remains at those temperatures is the matter itself, the atoms, the electrons, the nuclei. They are all still there, carrying the same charge and mass and spin that they carried in the heart of a flame. A carbon atom at 1 picokelvin is the same carbon atom that, in a different arrangement and at a different temperature, participated in the combustion of methane. The atom does not remember. It has no history, no allegiance to a particular phase or process. It simply is in whatever state its current environment dictates. And perhaps that is the most honest answer to the question. Fire does not become solid at any temperature. Fire ceases to exist at low temperatures because the process of combustion cannot be sustained. But the atoms that fire rearranges, the carbon and oxygen and hydrogen that pass through the reaction zone and emerge in new configurations, those atoms are indifferent to temperature. They can be gaseous in a flame and solid in a cryogenic crystal and quantum, coherent in a condensate at nanokelvin temperatures. They pass through states of matter the way travelers pass through cities, temporarily adopting the character of each one, defined by none of them. The fire was never a substance that could freeze. It was an event, a transient rearrangement of matter driven by chemical energy. And like all events, it belongs to a time and a temperature and a set of conditions that, once gone, cannot be recovered by simply turning down the thermostat. The universe does not become simpler at its extremes, it becomes stranger. The very low temperatures that the question invokes do not merely freeze the familiar world into stillness. They reveal a different world, one governed by quantum mechanics rather than classical thermodynamics, one in which the categories that organize our everyday experience, solid and liquid and gas and fire, dissolve into a more fundamental and more alien description of reality. At the bottom of the temperature scale, the question of whether fire can be solid is not answered. It is dissolved, replaced by a set of questions that the original framing could not have anticipated, questions about quantum coherence and tunneling and the nature of matter itself in the absence of thermal motion. And that, perhaps, is the most valuable thing that an extreme question can do. Not answer itself, but reveal, by the pressure of its own logic, the boundaries of the framework in which it was asked.